So far, we've used valence bond theory to explain that bonding occurs by overlapping half-filled orbitals, and we've used hybridization to explain how orbitals can make the shapes predicted by Vesper theory and observed by experimentation. However, there are a few properties that still can't be explained by just valence bond theory and hybridization. One of these properties is paramagnetism. Something that is paramagnetic contains at least one unpaired electron and is attracted to a magnet. The opposite of paramagnetic is diamagnetic. Something that is diamagnetic does not contain unpaired electrons and is weakly repelled by a magnet. When we draw the Lewis structure for the O2 molecule, we draw it with all of the electrons in pairs. However, when we test oxygen with a magnet, we see it is attracted to it, indicating that oxygen is paramagnetic. We need a bonding theory that explains the paramagnetism of oxygen and other molecules. That bonding theory is molecular orbital theory. We have already seen constructive and destructive interference with light. Remember the double slit experiment. It turns out that electrons and orbitals can also behave as waves and have constructive and destructive interference. When two atomic orbitals combine, they can either interfere constructively or destructively, just like light. When orbitals combine constructively, a bonding molecular orbital is formed. When these bonding molecular orbitals have electrons in them, it strengthens a bond within the molecule. This is because the electrons are mostly found between the two nuclei and act like glue, holding the two atoms next to each other. When orbitals combine destructively, an antibonding molecular orbital is formed. When these antibonding molecular orbitals have electrons in them, it weakens a bond within the molecule. This is because the electrons are mostly found away from the two nuclei, and they are essentially pulling the two atoms apart. To denote an antibonding molecular orbital, we put a star next to it. When an s orbital from one atom combines with an s orbital from another atom, they produce a sigma bonding molecular orbital with electron density between the two nuclei and along the internuclear axis. This is similar to overlapping s orbitals making a sigma bond in valence bond theory. However, in addition to this bonding molecular orbital, an antibonding molecular orbital is also created. It is a sigma antibonding, sigma star, molecular orbital because electron density is along the internuclear axis, but pointing away from each of the atoms. P orbitals oriented along the internuclear axis can also combine constructively and destructively to make sigma and sigma star orbitals. If the internuclear axis is considered to be the x-axis, then this occurs with px orbitals. Again, constructive combination makes bonding orbitals, which strengthen a bond within the molecule when they are filled with electrons. Notice the electrons are mostly located between the two nuclei and again act like glue holding the atoms together. Destructive combination, on the other hand, makes an antibonding orbital, with the electrons mostly pointing away from the two atoms and pulling those atoms apart. This particular set of orbitals are sigma bonding and sigma antibonding, because the electrons are still along the internuclear axis. Other p orbitals in the molecule are not pointing along the internuclear axis. Instead, they are either above, below, or in front of, behind the internuclear axis. When these combine, they make pi bonding and pi antibonding molecular orbitals. The pi bonding molecular orbitals have electrons above and below the internuclear axis, but mostly between the two atoms. The pi antibonding molecular orbitals have electrons above and below the internuclear axis, but mostly pointing away from the two atoms. The orbitals that combine have to be parallel to each other. Py can combine with Py, Pz can combine with Pz. In summary, bonding molecular orbitals are produced from constructive combination of atomic orbitals. They increase the electron density between the atoms and can be either sigma or pi. Antibonding molecular orbitals are produced from destructive combination of atomic orbitals, decrease electron density between the atoms, and we designate them as either sigma star or pi star. Similarly to how we have drawn atomic orbital diagrams for one particular atom, we will be drawing molecular orbital diagrams for a molecule. There are a lot of similarities to what we have already done. Just like with our atomic orbitals and hybrid orbitals, each molecular orbital can hold up to 2 electrons. Just like atomic orbitals have a specific shape, spherical, dumbbell, clover, etc., and hybrid orbitals have a specific shape, generally a large lobe and a small lobe, molecular orbitals also have a specific shape. Just like atomic and hybrid orbitals had specific energies, so do molecular orbitals. As we fill in our molecular orbital diagrams, we will still follow the Aufbau principle, start at the bottom and work our way up. We will also be following Hund's rule. Any time that we have orbitals that have the same energy as each other, we will put the electron in unpaired first, then pair them. Here's an example of a molecular orbital diagram. On the left and right sides, we have drawn the atomic orbital diagrams of each beryllium atom making up the bond. In the middle is the molecular orbital diagram of the 2 berylliums bonding together. As the atomic orbitals combine together, they create both bonding and antibonding orbitals. The bonding orbitals are always lower in energy than the original atomic orbitals. The antibonding orbitals are always higher in energy than the original atomic orbitals. Notice we have not included the core 1s electrons, but are focusing just on the valence electrons which are available for bonding. Each beryllium should have 2 valence electrons because beryllium is in group 2a. However, because we are doing the molecular orbital diagram of the beryllium plus 1 ion, we need to remove 1 electron. To account for the lost electron, 1 electron has been taken away from one of the beryllium atoms. We want the number of electrons in the atomic orbitals on the outside of the diagram to equal the number of electrons in the molecular orbitals in the middle of the diagram. As we fill the electrons on the outside of the diagram to the atomic orbitals, and in the middle of the diagram to the molecular orbitals, we follow the Aufbau principle and Hund's rule. Each orbital, whether atomic or molecular, can hold up to 2 electrons.